So say you have a short exact sequence of modules 0 a b c. To this sequence you apply this functor home of d this. So this functor is left exact. This is also covariant. We want to make this functor exact. So to make this functor exact, you will have to put a 0 here, but that would mean that this map has to be an epi or a surjective map. So to make this map surjective, it means if there is a function f here, you should be able to lift this f to some g right here. So if you can make this left exact functor exact, then we call this module D as projective module. So this functor has D in right here. Now we talk about injective module. So on this short exact sequence, you now put this home functor where D is some module. Now this is a contravariant functor, so it is going to reverse the arrows. So you see the arrows have reversed, but this is also left exact. So notice that the arrow is going in. So the arrow looks at on the right side, but this is called left exact because arrow is going in. So we want to make this exact. So that means we want to put a 0 right here. So to put a 0 right here, you have to make sure that this map becomes surjective. So becoming surjective means that say there is a function f here, you should be able to lift this f to some g right here. So if you're able to lift this f to g right here, you have a injective D module. So this is what injective means. Now flat. So if you try to tensor like this, you apply this functor to this short exact sequence of modules, what you get is a right exact. So this will give you right exact. So this naturally happens. Now what if you want to make this exact? To make this exact, you have to put a 0 right here. So right exact means that you have the 0 going out is right here. So to put a 0 here, you have to make sure that this map here is injective. So that is all. You have to show that this map is injective. So if 0 is not here, this map may not be injective. So if you can show that this map is injective, then you have a flat module. If this functor D tensor with this is exact. Now there are a bunch of results which we want to talk about. So the direct sum of this di is projective if and only if each di is projective. So this projective, so let us prove this result. So this result is going to use this property right here. So this is natural, you just take each of the maps phi I from di to a. So you take this map as phi I and you put them together in the direct product sense. So to prove this, notice that I'm just going to replace d with this direct sum here. So we have to show that this thing is exact if and only if this functor here is exact for all I. So let us see this. So we're going to apply this to this. So say if this is exact, so this is projective means, this module is projective means that this functor should be exact. So you will get home of now each of these terms is nothing but the same as this direct product. Here you get and here you get again you have direct product. So we are using this equality right here, and this holds if each of these, for all I, this holds. So for all I, you have to show that each of these sequences is exact. Now, but if you prove each of the sequences exact, that means each di is projective. So similarly, you can show for this product here. For that, you will use again this. So now it just becomes, since you're in the second part, it becomes contravariant. And then similarly for flat, you will show that the tensor products splits like this. And again, so each di is flat. So this direct sum is flat if and only if each of this di is flat. For that, you use this result. So you just, for flatness, we will use number 3 here. So exactly the same way you write down the sequences, and that is what you will get. Now, an important result is this: if you have an R module M, then homomorphism from R to M is just M. Yeah, so homomorphism from R to M. So to say this is some map F. Obviously, it's an arrow from R to M. What it does is takes 1, you evaluate it at f of 1. Obviously, you end up in a module. So this homomorphism R to M is just M, with f getting evaluated at f of 1. And R tensor M is just M. This is from the tensor product. Now notice that since free modules are direct copies of underlying rings R. So free modules are nothing but direct copies of underlying rings R. So direct copy something like this. So there are multiple copies of R, say. We see that the free modules are projective and flat. Now you're just using this property right here and this property here. So instead of di, you're writing ri, and instead of this di here, again you're writing ri. So this ri is nothing but copies of R, so something like this. So these are free modules, so that is what you are using. So this is important. Again, free modules are direct copies of underlying rings. So free modules are projective and they are flat. So again, we are using this property here and this property right here. So yeah, that is pretty much it. I mean, in order to check it, you should just write the sequence for yourself and see that what I'm saying makes sense. It's exactly copying these two 1 and 3 here, but still you should check. Now this is very important here, enough projectives. So for every R module, say A, we can construct a surjective map from P0 to A. So where P0 is a free module. So free on A as a set. So you can always have a surjective map like this. What you do is you take all the elements of A as a set and you generate a free group out of it. So it is free on elements of A as a set. And this surjection here, this comes from ID map from A to itself. So the copy of A inside P0 to A itself. So because you have, this is just a free module on all the elements of A if you can't find anything else. And then you can just map these elements of A to module A, using the ID map. And so ID map will at least make sure that you have surjection. Anything here will come from something in P0. So that is pretty much it. And enough projectives means that this, for every R module you can find something P0 here, which is free module. And since free modules are projective, we are going to use this condition later for some free resolutions. We will always say, okay, pick up any R module. So you will say, okay, I pick up R1. So I will say, okay, I will give you a projective map, surjective map from a projective module P1. Then you say, okay, I will pick another R module R2. I'll say, okay, I will give you another projective P2. These projectives are nothing but free modules, and since free modules are projective, we are just calling them P1, P2, so on. So you pick up any R module and I will give you a corresponding projective module, and that's why they say there are enough projectives in this this R module. Say if R module formed a category, there are enough projectives in it.